Hello sir and ma'am, my name is Sanskar Gupta. I along with my teammate present our AIFA project. The topic which we had chosen is Monte Carlo tree search. So idea for the same came through one of the topic of our course which is alpha beta pruning algorithm. So when you implement AI for games, the most important factor is the quality of the game state. The classic approach uses heuristic domain knowledge for the same. So when we build adequate evaluation function using heuristic knowledge for non-terminal game state, it is a very complex task. Here comes MCTS in the role, which is very efficient than as compared to a classical approach. In some previous year, it has been applied successfully to many of the games. Now we will discuss the characteristics of the MCTS. So initially, it was proposed by coaches and Column in 2006 as an algorithm to make strong game player for games like Go. It is a iterative decision-making algorithm that searches the state space and builds up a statistical evidence. It is a very robust approach for designing game-playing bots and solving sequential decision problem. And one of the important thing which distinguish it from the classical approach is a heuristic search, which doesn't require knowledge of any other knowledge than the game rules. Though we can implement heuristic knowledge to make this algorithm more efficient. So now we will discuss the steps of the MCTS, starting with the selection, then expansion, simulation, and at last backpropagation. So in selection, we start from the root node, and at each step we select one of the child node, and then we go to the expansion, and from that child node we create at least one node if that the child node is not the leaf node. So then we perform a complete random simulation. Then we perform a random simulation that is reaching the terminal state and fetches the payoff. This is what known as the Monte Carlo part of the algorithm. And at last, we update all the nodes which is in the path. So now we'll discuss each of the step in a well elaborated manner. So here we start from the selection. Here the values which is in the tree is like it is 11 by 21, which stands for the probability value, uh, winning probability. So when we go with this action, we have won 11 times if we have played 21 times. So how to select a node? So what is the one can think is most basic is that to go with the one which has the highest probability. But this may not be the best case. So here we uses a tree policy, which is also known as a selection policy, which whose main objective is to maintain a balance between exploration and the exploitation part. So by exploitation, we mean that the go with the node, which has been go with the node which has been well tested, and by exploration, we go with the node which has not been well tested. So if we go with this, so we have 7 by 10, 3 by 8, and 0 by 3. So we can say that the 7 by 10 is to go with the exploitation part, and 0 by 3 is to go with the exploration part. So talking about the method, so the most common is the UCB method that stands for upper confidence bound. Here we assign UCB value to all the child node, which has to be from which we have to select. And by using this formula, where which is a QT of A plus C times root of log T by NT of A. Here, QT by A stands for the probability value. So let's say if we are finding a UCB value for this, 7 by 10 is the probability value, and the T stands for number of time the parent node has been selected. So which is 21, and NT of A is number of times this child node has been selected, which is 10. So there are two terms over here we can see. So where QT of A focuses on the exploitation part, whereas this term focuses on the exploration part. And after assigning UCB value to all the child node, we select the one which has the maximum UCB value. So this was with the UCB case, and there are also other methods like rapid value action estimate, So we haven't discussed these because they aren't that much common as UCB. So we haven't discussed these. For next step, I would like to call Riju. He will discuss the further steps. Thank you.
So we demonstrated how we can select our next node based on probabilistic method in selection. Now, what happens when we reach a terminal state? So we add one more child to this node, which is, and this step is expansion. So there may be some rare conditions when this expansion reaches terminal state. So that time we directly skip to backpropagation, which we'll see further. So next comes the question: how do we calculate the probability of the new expanded node? So here comes simulation. What we do is we play some random moves from this node until a win or a loss is recorded and update that record. So and this is simulation. Next comes the final step, which is backpropagation. So we have recorded the um, win or loss from the backpropagation. Now, how do we update it to all the nodes that were visited? So here comes the backpropagation, which helps us to update all the statistics that are recorded back to the game tree. Thank you. And next, over to Anjali.
Now let us understand the MCTS as an example of keyword research. In order to make the analysis easy, we have reduced the set space with just 3 moves per player. So this defines the initial configuration of the board in which player A will be making a local move. Now since it doesn't have any child, so it will expand a node corresponding to move X, and let's suppose that the move by B leads to the winning state of A. So it will propagate back and update the node's value. We can see that the winning percentage here corresponding to move X is 100% after first simulation. Now, let's say in some second simulation, player B takes an alternative path, which ultimately leads to the losing state of player B. So accordingly, it will propagate back, update the nodes value, and now we can see that the move corresponding to X, the winning percentage now is decreased to 50%. Similarly, when we see other combination of moves, we might see the decrease or increase in the amount, the percentage of winning of player A, depending upon the kind of moves which are taken by player A and player B, and the number of simulations. Now, since it leads to the winning state of it, so the winning percentage has increased to 66.7 percentage. Now, since the opening move corresponding to X has been explored multiple times, so we seek to expand other choices corresponding to Y and Z. Let's say the Z node has been expanded. So, depending upon the goal state which are achieved at the end, the node value is again updated, and we can see that the winning percentages now become to 50% corresponding to opening move of Z. So after some simulations are made, we have reached at this tree state. Now this is certainly not the best model which we can have, but this is certainly the better version of the previous models which we had obtained after a few simulations. Now, if another simulation were to be made, then it would do its selection of nodes based on the formula which depends on exploitation and exploration. Exploitation is a selection of nodes which are appearing more promising, and exploration is a selection of nodes which are appearing less promising and are relatively explored less in number. So if we let the simulation increase in number, then we can see the increase in the size, and also we can have better and better strategies which would make it difficult for player B to win against player A. So it's moving down to its application. We can have classic board games such as two-player deterministic games, which can involve MCTS in its application, and MCTS application can also be found in modern games like Settlers of Catan and video games like Spring RTS game. So apart from these research applications, we can also have Monte Carlo simulation applications in several places such as determination of pi and path tracing techniques. So in this simulation, we have a marble dropping device that moves randomly above the table and drops the marble. Above this table, we have two boards, one of square cross section and one of circular cross section, with displays with this case on them, which displays a number of balls in the respective balls. So if we let the simulation evolve for a longer time, then we see that the ratio of number of balls in the circular cross section to the number of balls in the square cross section, it comes closer to the value of pi. So basically what happens is that when we drop the marble at random location, the probability of marble to end up at one of these balls is directly proportional to the area of cross section of the pole. So if we repeat it over and over again, we can see that the number of poles is directly proportional to Bohr's cross section area. And if we take the ratio, then it comes out to be ratio of area of the circular to the square cross section, which comes out to be approximately equal to pi. And also now moving down to its second application, which is a path tracing technique. We can see that to get an accurate image, we need to have how much light rays hit different areas of the scene. But it's not an easy task to determine it, as the surface can literally scatter the light in multiple, infinitely many directions. So to find out the light rays hitting in an area, we'll need to evaluate all possible paths hitting that. We'll need to evaluate all possible light paths and take a fraction of the light path which hits at that particular area. But it's literally impossible to follow all the light paths. So since we can't simulate all the light paths, so we'll try to select some random some of the directions that appear after the light has been scattered from a surface. So let's say we'll take the sample path and have this direction uh, over over a point. But as we know that taking less samples would not give us accurate answers, so we'll have more such samples which would be hitting at a point. Thus, it would increase the intensity of the light at that point and would lead us to the accurate answer. So we say that as the number of sample increases, so the quality of the image also increases as we have more samples in our box. So this was all from the example and application section.
Good evening. My name is Nikhil Baskiar and I shall be explaining to you the advantages and the disadvantages of the Monte Carlo tree search algorithm. Firstly, the advantages. It can be seen that it is simple to implement with a vast range of applications ranging from scientific uses like calculating the value of pi to a number of games with little modification, and makes MCTS a potential boom for general game playing. In particular, pure Monte Carlo tree search does not need an explicit evaluation function. Simply implementing the game's mechanics is sufficient to explore the search space. As such, Monte Carlo tree search can be employed in games without a developed theory or in general game playing. The heuristic nature of Monte Carlo tree search means that it does not require any strategic or tactical knowledge about the given domain to make reasonable decisions. The algorithm can function effectively with no logic of a game apart from its legal moves and end conditions, and can find its own move and learn from them by playing random playouts. Heuristic algorithms are practical, serving as short and feasible short-term solutions to planning and scheduling problems. In computer science, an anytime algorithm is an algorithm that can return a valid solution to a problem even if it is interrupted before it ends. The algorithm is expected to find better and better solutions the longer it keeps running. MCTS algorithm is one such algorithm which reaches the optimal solution through a large number of random sampling of the game tree. The algorithm can be halted at any time to return the current best estimate. The search tree built thus far may be discarded or preserved for future reuse. MCTS's continual improvement over time can also be exploited to make the algorithm play a game at varying levels of competency. Lower difficulty levels are achieved by stopping the algorithm before it has a chance to improve the initial set of recommended moves. MCTS performs asymmetric tree growth that adapts to the topology of the search space. The algorithm visits more interesting nodes more often and focuses search time in more relevant parts of the tree. This makes MCTS suitable for games with large branching factors such as 19 times 19 Go. Such large combinatorial spaces typically cause problems for standard depth or breadth based search methods like minimax, where exploring each child node would become very computationally expensive very quickly. But the adaptive nature of MCTS means that it will eventually find those moves that appear optimal and focus its search efforts there. Now I shall speak about the disadvantages of the Monte Carlo tree search. Memory usage is also an important constraint in commercial applications, particularly on mobile platforms or when there are many AI agents. While MCTS takes less memory than Minimax algorithms, as the number of random simulations performed by MCTS increases, the algorithm converges to Minimax and tends to explore a larger number of branches, as the best choice of child nodes become Although MCTS has proved to be useful for Go, it is worse in chess compared to traditional minimax techniques. This is because chess has many situations where the best initial move results in success only when it is followed by a very specific series of subsequent moves. But the average series of subsequent moves has poor results. In these situations, MCTS focuses its initial effort on other moves that are not the best solution. It doesn't focus on the best initial move until after it has discovers the specific series of subsequent moves that result in success. This means there is a chance for MCTS to start exploring parts that may appear optimal to it, but not truly the optimal solution. It may even play move that looks superficially strong, but that actually lead to a loss via a subtle line of play. Such trap spaces require thorough analysis to be handled correctly, particularly when playing against an expert player. However, MCTS may not see such lines due to its policy of selective node expansion. The MCTS algorithm in its basic form can fail to find reasonable moves for even games of medium complexity within a reasonable amount of time. This is mostly due to the sheer size of the combinatorial move space and the fact that key nodes may not be visited enough time to give reliable estimates. MCTS algorithm needs a huge number of iterations to be able to effectively decide the most efficient path. For example, the best Go implementation can require millions of playouts in conjunction with domain-specific optimizations and enhancement to make expert moves, whereas the best general game-playing implementations may only make tens of domain-independent playouts per second for more complex games. For reasonable move times, such general game playings may barely still have time to visit each legal move, and it is unlikely that significant search will occur.
Next, we come to improvement of MCTS. So dozens of MCTS enhancements have been suggested to date. These are generally we described as being either domain knowledge or domain independent. Coming to domain knowledge specific to current game can be exploited in tree to filter out implausible moves or in the simulations to produce heavy playouts that are more similar to playouts that would occur between human opponents. This means that playout result will be more realistic than random simulation and that nodes will require fewer iteration to yield realistic reward values. But it has some drawbacks. Domain knowledge can yield significant improvements at the expense of speed and loss of generality. Now coming to domain independent. Domain independent enhancements apply to all problem domains. These are typically applied in the tree. Although some apply to simulations, uh, domain independent enhancements do not tie the implementation to a particular domain. The maintaining generality and are hence the focus of most current work in the area. Next, these are the references that we have used. The first one is Monte Carlo Tree Search, a new framework for game AI. And the second one is Monte Carlo Tree Search for a review of recent modification and applications. Thank you, and with this we conclude our presentation.